New India's vision is to become a developed country and Atmanirbhar Bharat by 2047. To achieve this goal, we need to be self-reliant for our energy needs. According to reports from the Lawrence Berkeley National Laboratory, we import 90% of the total oil demand, 80% of the industrial coal demand, and 40% of the total natural gas needs. Another study, conducted by the Council on Energy, Environment and Water, found that to reach net zero emissions by 2050, fossil fuel demands have to be reduced to 5% by 2050. 83% of total electricity demand has to be generated from renewable sources. Our government has also set a target to achieve net zero emissions by 2070. To achieve this target, biofuels will play a critical role. Ministry of New and Renewable Energy, the Government of India has initiated a national bioenergy program. Under this program, the government aims to develop small and medium-sized biogas plants in rural areas. These biogas plants will be used to generate power in the range of 3 kilowatts to 250 kilowatts and also generate thermal energy for domestic use. As we aim to generate electricity from biogas plants, we need to look for indigenous technology which more sustainable and can serve both the purposes of power and thermal energy. Micro gas turbine is that technology for distributed power generation. These are smaller versions of the conventional gas turbine systems. They operate on the same principle as traditional ones. Microgas turbines are smaller in size and have a high power-to-weight ratio. They range from a few kilowatts to hundreds of kilowatts. They can be used as the power backup in hospitals, colleges, movie theaters, etc. They can also be used as range extenders in electric vehicles to increase the range of the vehicles. Most of the mobile towers are located in remote areas which can be powered by micro gas turbines. Now we will discuss the layout and working principle of micro gas turbines. The main components are the compressor, recuperator, combustor, turbine and generator. Atmospheric air is compressed in the compressor and passed through to recuperator where it is heated by the incoming exhaust gases. Preheated air is supplied to the combustor. Preheated air and fuel is mixed in the combustor and combustion takes place. Exhaust gases from the combustor are supplied to the turbine. Exhaust gases rotate the turbine shaft which drives the generator to generate power and compressor. Exhaust gases then reach the recuperator to heat the compressed air. This project is dedicated to combustor design. So now we will look at the combustor layout and its different components. The key components of an MGT combustor are a swirler, fuel injector, fuel supply line, combustor head, liner, outlet of the combustion chamber, spark plug, outer casing, and air intake plenum. Preheated air is supplied to the combustion chamber through the air intake plenum from where it passes through and is divided into two parts: primary and secondary air. Primary air goes through the swirler and creates a recirculating zone inside the combustor in the primary zone. Fuel is supplied in the combustion chamber, where it is mixed with the primary air in the recirculation zone created by the primary air. Now, ignition takes place and combustion takes place in the primary zone of the combustor. Secondary air is supplied through the annular gap of the liner and the casing. Secondary air goes inside the liner through the holes provided. There are 2 rows of holes provided in the combustion chamber. These 2 rows of holes divide the combustion chamber into 3 respective parts. One is primary zone, where main combustion takes place, and secondary zone where air from the first row of holes mixes with the exhaust gases coming from the primary zone. It is expected to achieve complete combustion in the secondary zone. The last is dilution zone, where the air coming from the second row of holes is utilized to cool down the exhaust gases before they exit the combustor. The exhaust gas temperature has to be reduced because of the material constraints of the turbines. It is important to understand the requirements of the combustor. The combustor should be compact. It should have a low pressure loss. Combustors should have wide stability limits under different conditions. It should be able to operate on different fuel compositions. It should be highly efficient. Operation of the combustor should be easy and smooth. All these requirements of the combustion chamber impose certain design constraints which come as design factors of the combustion chamber. Design factors of the combustor are pressure loss factor, combustion efficiency, pattern factor, fuel jet mixing, size of the recirculation zone, and hot pressure loss. Based on the design challenges, these are the objectives set for the project to reach the goal of designing a combustor for a micro-gas turbine system fueled with biogas. The first objective was to design a combustor. Improvement of the designs through numerical simulations. To check the operation of the combustor with different compositions of biogas. Fabrication of the combustor based on the numerical studies. Performance validation of the fabricated combustor. The scope of the work is decided in order to achieve the objectives. First, validation of the numerical techniques will be done. To check the swirler requirements and the air and fuel flow rates, a 2D axisymmetric model of the combustor is selected. Once these parameters are fixed, a 3D model of the combustor is modeled and studied. Parallelly, lab-scale model of the burner is developed for testing the swirlers and fuel injectors experimentally. Finally, the first prototype of the combustor is designed, which has optical access to the flame. After this, ignition tests are carried out on the combustor at different fuel compositions and different air flow rates. To validate the numerical methods, two different types of well-studied burners have been selected. First is the Sydney swirl burner. The computation domain used for numerical modeling is shown. The second is the turbomica burner, which has a radial swirler base burner and produces lifted flames. Both velocity and temperature field distributions are shown here. It was found numerical techniques used were able to reproduce the results as obtained in experimental results. Here, flow passing through the axial swirler is shown. The blades of the swirler are bent at a particular angle based on the required strength of the recirculating zone. Now we will see the flow inside the radial swirler-based turbomica burner. Here, the flow development inside the combustion chamber can be observed. Incoming compressed air passes through the swirlers and starts developing the central recirculation zone and outer recirculation zone at the corner of the combustor. Central fuel jet is obstructed by the central recirculation zone and enhances the mixing. The momentum ratio of air and fuel plays a critical role in fixing the size of the combustor. The effect of the momentum ratio is shown for fixed thermal power and fixed swirl strength. Here it can be seen, when the momentum ratio is low, the flame does not form inside the combustor. A very small, high-temperature region is observed inside the combustor. Once the momentum ratio is increased by one order as compared to the first case, flame is well within the combustor liner. With the increase of momentum ratio, the amount of air available is increased for fuel. This increases the size of the recirculation zone, which leads to better mixing of fuel and air. After understanding the effect of the momentum ratio, now let us understand the effect of swirl strength at the fixed momentum ratio. Here it can be observed that, with an increase in the swirl strength, the flame moves upstream toward the air and fuel injector. For swirl numbers 0.5 and 0.8, there is not much difference in flame shape and size, but once the swirl strength increased to 1.5, the flame is moved above the fuel injector. It forms a flame ring around the injector, which is not good in the long run because the fuel injector will be damaged due to continuous exposure to high temperatures. After understanding the effect of momentum ratio and swirl strength, the effect of fuel composition is shown. Methane and BG60 have been considered as the two fuel compositions. BG60 signifies the composition of biogas, which has 60% methane and 40% of carbon dioxide. It is well known that carbon dioxide is a non-combustible gas that will act as a diluent in biogas combustion. To generate the same amount of thermal energy, a higher volume of BG60 will be consumed. Because of the presence of carbon dioxide, the fuel flow rate will be increased as compared to the methane case. Here it can be seen that for BG60, fuel penetration in the recirculation zone is higher as compared to the methane case, but the good thing is flame is still within the liner of the combustor. With numerical modeling, all the necessary parameters for combustor design are fixed. Now combustion analysis on a lab-scale burner is shown. For the experimental study, different type of axial vane air swirlers and fuel injectors are designed. To check the flame stability under different operating conditions, a lab-scale burner setup is developed. After the development of the lab-scale burner setup, The non-reacting flow field inside the burner is characterized using the laser Doppler velocimetry technique. After this, the effect of the fuel injector position on the flame shape and stability is tested. It was found that when the injector is above the exit flame, soot formation takes place, leading to a yellow flame. After fixing the fuel injector position, methane flames under different air flow rates are tested. It can be observed here, with an increase in the equivalence ratio, flame height is continuously increasing. At an equivalence ratio of 0.4, a flame is attached to the fuel injector. The same tests under the same operating conditions are conducted with biogas fuel, BG60. Here also same trends can be observed for BG60 as well. At an equivalence ratio of 0.4, the flame for BG60 is lifted as compared to the methane case. With an increase in the equivalence ratio, flame height increases continuously. The lower the equivalence ratio, the higher the stability of the flame. After completing the study of the lab-scale burner, an optically accessible combustor is developed to check the flame forming inside the combustor. Both the liner and the outer casing are made of quartz, which is optically accessible and can sustain high temperatures. The main purpose was to check whether the flame was inside the combustor or not. It can be seen that the flame is well inside the combustor. When the performance of an optically accessible combustor is assured, ignition tests on the first prototype of the combustor are done under the influence of secondary air flow rates. Ignition tests are conducted at 5 kilowatts of thermal power at a fixed primary air flow rate. The main aim was to check the influence of the secondary air on the ignition of the biogas fuel. Secondary air flow rates are varied from 120 lpm to 180 lpm. All the tests are conducted on BG60 fuel. It can be observed that successful ignitions have been obtained for all the 4 cases. Successful ignitions were obtained up to 180 lpm of secondary air flow rate. Here is one case of a misfire during the ignition tests. It can be seen that there is ignition, but it did not convert into a fully developed flame, which shows that this particular case misfired during the ignition. The top view of the fully developed, swirling flame inside the combustor can be seen here. The swirling nature of the flame is visible. After successfully testing the first prototype of the combustor, the final combustor was developed. All the components liner assembly, plenum, outer casing, swirler, fuel inlet, and air inlet of the final combustor model are shown here. Ignition tests on the final model were conducted with a common air inlet. Earlier ignition tests were conducted with separate air supply. In real life, air is supplied from the common inlet connected to the compressor. Ignition tests were carried out on methane and to compositions of biogas. Here, successful ignition tests conducted at the upper limits of the air supply are shown. For methane, successful ignition was obtained for a global equivalence ratio of 0.3. For BG60 upper limit of air was a global equivalence ratio of 0.4, and for BG50 upper limit of air was a global equivalence ratio of 0.6. Thus, successful demonstration of the microturbine combustor operated under different biogas compositions is shown. The project could successfully achieve its target. All the thanks to the research students who worked on this project under the guidance of Dr. Sudipto Mukhopadhyay. A special thanks to Center of High Technology for their support for the project.